Surface integral of first kind. Let us have some smooth surface omega that is specified explicitly, and we have some function f of x, y, z that is continuous on this surface omega. Let us split omega into pieces omega I. Each piece has area delta sigma I and diameter di. And inside each piece omega I, we select average point M with coordinates psi I, eta I, phi I. And then we form an integral sum I from 1 to n f of mi by delta sigma I. If there exists finite limit when maximum of diameter tends to 0 and number of pieces tends to infinity, we call this sum, this limit of a sum, surface integral of first kind. Properties. First one is linearity. If we have surface integral of first kind of some alpha f plus beta g d sigma, we will get alpha integral by surface of f d sigma plus beta integral by surface of g d sigma. Second property, if we have some surface omega that consists of union of two pieces without any internal points, common internal points, then we can calculate integral by omega of f d sigma as integral by omega 1 f d sigma plus integral by omega 2 d sigma. And third property, integral of first kind, surface integral of first kind equals d sigma equals area of omega, of the surface omega. Let us try to calculate area of a surface which is bounded by smooth curve L. Surface, we will name it omega, and f of x, y is continuous on this omega and its derivatives are also continuous. Let us have this surface set in three-dimensional coordinate system, and let us project this object, this surface, on xy, on a plane. And this projection we'll call D, and it will be bounded by gamma. It will be bounded by curve gamma. Now, we can split omega into pieces, omega I, and these pieces will be projected on the plane, region D, inside a piece di. Here we select a point mi, and inside di we select point ni. Mi has coordinates psi I eta I phi I, and phi I is f of psi I eta I. So we can build a tangle plane that runs through points mi, and we'll have an equation z minus zi phi I will be derivative f by x of psi I eta I, x minus psi I, plus derivative f by y of psi I eta I, y minus eta I. This will be equation of a tangle plane. And we build this tangle plane and we select some piece di. di is a piece of this tangle plane. It has area delta di and diameter di, and this piece di projects on D, inside di. If we have smooth surface, we can presume that delta sigma I is approximately delta ti, and area of this surface is approximately again sum of delta ti. So we approximate this surface by planes, by pieces of planes. And now we can calculate this area S of omega as limit when di tends to 0, maximum di tends to 0 and tends to infinity, sum I from 1 to n delta ti. Let us consider this tangle plane. Here we have di, inside it we have mi. This angle is gamma I, and so this angle, inside this piece we have ni, and this vector is a normal vector to this plane. So if gamma I is an angle between OXY and this tangle plane, then delta ti will be delta Si divided by cosinus gamma I. So area of this piece will be area of this piece divided by cosinus gamma. So this vector n is calculated as f derivative by x and I by vector I minus f derivative by y and I j plus k. So delta sigma I is approximately delta ti, which is square root of 1 plus f derivative by x of ni square plus f derivative by y ni square delta si. And we can assume that d sigma is square root of 1 plus z derivative by x square plus z derivative by y square dx dy. If we have surface omega specified by f of x, y, z equals 0, then this vector n is plus or minus gradient of f. And length of this gradient is absolute value of gradient f is square root f derivative x square plus f derivative y square plus f derivative z square. So cosinus of angle between n and k will be f derivative by z absolute value divided by square root of this sum f derivative by x square plus f derivative by y square plus f derivative by z square. So from here we get that d sigma will be square root of the sum f by x square plus f by y square plus f by z square divided by derivative f by z absolute value, and everything is multiplied by dx dy. How do we calculate this object? If we have some omega specified by z equals f of x, y, and it projects on oxy into some region d ox y, then we have a formula: integral by surface of first kind f of x, y, z d sigma can be calculated as double integral by the projection of omega by onto oxy f of x, y, z of x, y square root of 1 plus z prime x square plus z prime y square dx dy. How can we apply this integral? Well, we can calculate areas of surfaces. Area of surface is surface integral of first kind by omega of d sigma. Second application, mass of surface. If we have some mu of x, y, z density, then m will be surface integral of first kind mu d sigma.